Hello students, in this video I'm going to derive the mathematical model or equation of motion for a mass spring system. Okay, this is known as a simple harmonic motion. You might also see this as an undamped-free model. That means that there's not going to be any frictional forces in our mass spring system. So before I delve into this derivation of this ordinary differential equation and all the units and all that stuff, let me just show you a little animation to give you a feel for this system. So here's our wall here, or ceiling, and here's the mass on the spring, and it's oscillating up and down, right? So this green dot represents this green dot that's circling around here. So you see that you're going to get some kind of, you're going to get oscillatory motion, and you could expect with this kind of harmonic motion, you see sines and cosines then, right? I'll return to this notion of phase space and velocity later in this course, in a later video. But right now I just want you to focus on this picture here. So you have this block, and there is the force that is contained by the block and its motion, right? So if you imagine if you were sitting under this block where my arrow is, my cursor is, when the block comes down, it'd smash you, right? It just smash right into you there. Now, what keeps the block from just plummeting down into the abyss? Okay. So it has this force that smashes you, right, from its force of motion, but there's some other forces acting on this block. Now you might say, okay, well, there's the force of motion, there's also the force of gravity that's pulling it down, and then you would notice that, oh, there's this spring here, and this spring is pulling the block up. Well, okay, what keeps the block from crashing through the ceiling? Okay, well, again, you'd say, well, there's going to be gravity pulling it down, and then the spring is going to, there's a restorative force from the spring that's going to push it back. Okay, so that really, keep that in mind, and just go with your intuition there. You will have captured all of the forces that are contained in this model, and you would have essentially gotten the derivation of this model. We don't have any air resistance in this case, so this block, as in this animation, we just keep bouncing up and down forever. So let's go back to my diagram here. So without a block, the spring has its natural length, okay? And with the block attached, it would, at rest, it would just sit there, wouldn't move. And then we're going to pull the block a little bit further, stretch it, and then it's going to want to snap back and then get into that oscillatory motion. Okay, so that's the three stages you see here. This is what the model looks like. I will derive this equation for a moment. N is going to be the mass. K is something called the spring constant. The units of M, we'll call them kilograms, just so I have something to refer to. The units of K will be kilograms per second squared. And the units of x will be meters, m, not m the mass, m meters. All right, so let's continue with this. So little l is the natural length of the spring. Capital L is the amount where it's stretched, but it's at rest. It's not going to bounce. It's just going to sit there motionless. I'm assuming that downward is the positive direction. That's in the direction of gravity. Now, this line is the at rest. We call that equilibrium. So the only force acting on the block at this point is mg, right? That is the weight of the block. It is being, what keeps it from plummeting down into the abyss is that the spring is holding it up. And so there's a restorative force, the spring pulling upward, and that is given by KL. So we have mass, kilograms, meters per second squared is balanced by kilograms per second squared times the length, meters, so the units match up. Now at this point, this x, which is our position, is 0. So this is at rest, that's position 0. Now we're going to stretch this spring a little bit. And so there's a spring force when you stretch it. This distance, this little margin here, is the distance x. And since the restorative force wants to pull it upward, I'm going to put a negative sign there. That's why I needed to note that the positive direction is downward. So this is called Hooke's law. And this is saying that the spring force is a force acting in the upward direction, and then when it gets up to the top, it's going to push it downward. So it's acting in the direction opposite of the motion. So when we stretch it by this length x, we have the two forces that are acting on this block, of course, at this moment. Just holding it in place are the weight that's pulling downward and the restorative force that wants to sling this back upward. Now, there's no other forces acting on this block. Like I said, there's no frictional forces. There's no motor up here pushing it upward or downward, pulling it, cranking it up or pushing it downward. It's just, that's the only two forces acting on this. So once I let go, that's all we have is the balance by the force of motion. So the block's going to swing up, and then if you put something here, the block would bash into it, okay? And that that would be the force of the motion. So the force of the motion is balanced by the weight of the block wanting to pull it downward, and the restorative force wanting to always push it back to the equilibrium or at rest position. So you have the spring force, and then you have the force of the motion, which is your F equals ma. So the force is proportional to the acceleration of the block, and now if I just do some algebra, I'm going to distribute the k into the L plus x quantity here, and distributive property gives me minus KL minus KX, and then we're just going to do a small simplification here. Of course, given the at rest position here, I have mg equals KL. When I subtract KL from both sides, I see that mg minus KL is equal to 0, so this term is equal to 0. So that leaves us with minus Kx is equal to mx double primed, and that is the equation of motion. Mx double primed plus Kx is equal to 0. So that is undamped free motion for a mass springs system, and we will call that simple harmonic motion, SHM. All right, that's the derivation. Good luck.